All right, folks. So this video is going to be about significance tests for means. So t-tests. Okay. We did significance tests for proportions in class. All right. And I'll probably post videos that were made by somebody else to review that topic. And I'll post videos that were made by somebody else to review any other videos that I haven't made yet. This is probably the last video I'll be able to make this week. And then, any content that I haven't made a video on, I'll try and make that next week, but at least I'll try and get some con videos or something so that you guys have some examples to work on for any content that I haven't made a video on yet. All right, I just want to start, right? These are sampling distribution for means. These are all the formulas, right? So if they ask you some probability questions where they happen to be giving us the population standard deviation, we can use these formulas here in the middle. Oftentimes, we're not going to know the population standard deviation, which is why we'll either have to build a confidence interval or perform a significance test to see if the population mean is what we think it is or if it's something else. So oftentimes when we're doing inference, we have to use these formulas over here, which is just replacing the population standard deviation with standard deviations from samples. Okay, so this is where you can look on your formula sheet to find these if you're dealing with a significance test for means. So I'm just going to hop right into it here. This one I believe is going to be a one sample t-test. So we'll start with a one sample t-test. All right. This thing says regulations require that product labels on containers of food that are available for sale to the public accurately state the amount of food in those containers. Specifically, if milk containers are labeled to have 128 fluid ounces, and the mean number of fluid ounces of milk in the containers is at least 128, the milk processor is considered to be in compliance with the regulations. The filling machines can be set to the labeled amount. Variability in the filling process causes the actual contents of milk containers to be normally distributed. A random sample of 12 containers of milk was drawn from the milk processing plant line, and the amount of milk in each container was recorded. So part A says, the sample mean and standard deviation in this sample of 12 containers of milk was 127.2 ounces with a standard deviation of 2.1 ounces. Is there sufficient evidence to conclude that the packing plant is not in compliance with regulations? Provide statistical justification for your answer. Okay, so we took one sample. It's a mean, not a proportion. Okay, and they're asking us to provide convincing statistical evidence. So they must want us to conduct a one sample t-test, a one sample t-test. Okay, and whoops, come on, why won't this click in there? Let me type more. One sample t-test. All right, that's what we're going to be doing for this question. All right. So first we have to come up with some hypotheses, right? So the null hypothesis or the dull hypothesis, the statement of no difference, however you've, heard or read about writing a null hypothesis, is just going to be that the company is in compliance, right? This null hypothesis is always going to be like the status quo. So if we want to assume that the milk company is in compliance, we're going to say that the population mean is equal to the 128 ounces that it needs to be in compliance. Okay, and then the alt hypothesis. All right, let's see. It says, they give us some information and they say, is there sufficient evidence to conclude that the packaging plant is not in compliance? They told us in order to be in compliance, the average amount of ounces in each milk container needed to be at least 128, right? So we'll run the test assuming that they're in compliance and the mean is equal to 128. But the alt hypothesis then in this case is going to be that the mean is actually less than 128 ounces, okay? Now, do we have, actually first, why don't we write in some other important information, right? They told us that the sample size was only 12. Now, if you know about central limit theorem, you know that we can only say that a sampling distribution will be normally shaped if the sample size is bigger than 30. So we're clearly violating central limit theorem right now. However, this is one of those particular questions where we're going to violate central limit theorem. We don't have a big enough sample size, but they do tell us in the question the filling machines can be set to the labeled amount. Variability in the filling process causes the actual contents of the milk containers to be normally distributed. So they're telling us the population is normally distributed. Okay, so we don't have to worry about our sample size in this case, right? Central limit theorem is really useful for us when we're not sure what the population looks like, or if we know that the population is not normally distributed. We know any sampling distribution of means will be normally distributed if I have sample sizes bigger than 30. I'm violating that rule, but I know I'm sampling from a normally distributed population, so the sampling distribution will also be normally distributed, right? Now, do we have some evidence that this company is out of compliance? Sure, we do have some evidence because we took a sample of 12 and we found out that the average of those 12 was only 127.2. That is less than the 128 that's required for me to be in compliance. So I have some evidence, right? But is it strong enough evidence? Or is it so close to the 128 ounces that we're supposed to be at that we can chalk it up to random chance for these 12 particular, cartons of milk that we've sampled, and we don't have enough, statistical evidence to disprove that the company is not filling the containers up enough. All right. Another important piece of information that they gave us was the standard deviation for the sample. So I'm going to label that as SX, and they told us that that was 2.1. That's going to come in handy later. 2.1. And what level do they want us to run this test at? Okay, I don't think they tell us. It just says, is there sufficient statistical evidence? Is there sufficient evidence to conclude? All right, so they don't give us a significance level to run the test at, right? When they don't give you a significance level, the default is always going to be 5%. Okay, so now I guess we can go on ahead and we can check our conditions, right? This is all the setup. This is some of the important stuff, and we can check some conditions. No matter what kind of inference you're doing, one of the conditions is always, do we have a random sample? All right, so again, I've stated the procedure. I've laid out my hypotheses. I laid out any other important information that I might need to conduct this test. I forgot to define my parameter. I'll get back to that. Let's just check the conditions, right? Do we have a random sample? Let's look. Let's talk about these. Where do they tell us? A random sample of 12 containers. So check. Okay. Next one is the 10% condition, right? We don't want to violate independence. We don't want to sample too many containers. So I need to say that these 12 containers of milk is going to be less than 10% of all the containers of milk that are going to be produced by the factory on this shift or something like that, right? But I'll just write that statement like this. 12 is less than 10% of the population, right? And we'll check that off. And then 3, right? We're going to fail central limit theorem, but they tell us that the population is normally distributed, right? I'm just going to write normal because I don't have a ton of space and it's hard to write with the mouse. But you would write the population is normally distributed. They told us that in the question. All right, so pretty easy to check the conditions here. We didn't really have to do so much. The last thing I want to do here before we get to actually running the test, all right, is I want to define my parameter. So my parameter is going to be, I'll come back to that. My parameter is going to be mu, right? Population mean. This is the symbol for population mean. This is the symbol for sample mean. So we're going to say that this is equal to, and now I'll throw a text box in there, the true mean, let's call it, how do I want to say this? I guess I'll say the true mean fluid ounces of milk in the containers produced by the filling company. Okay, that's what we are trying to run this test on. All right, we're trying to see if we're in compliance, right? Is the true mean equal to 128 like it's supposed to be, right? Because they say at least 128. Or is it less than 128 and we're out of compliance? That's what they're asking us to do. All right, so I got my procedure, my hypotheses, other important information I'll need to run the test. I have defined my parameter, what it is we're running the test on, and I've checked my conditions, okay? So I'm going to come back to these formulas here in a second, all right? But before I do that, let's talk a little bit about the sampling distribution that we are going to run this test on. Okay, here is my sampling distribution. Wow, that is super ugly. Let me try again. Can I? Oh, there we go. I can get a straight line like that. And then no. I'm trying my best. It's like ridiculously hard to write with a mouse. All right. This is my sampling distribution of X bar, right? If I were to take many, many, many samples of size 12, right, and measure their average, amount of ounces of milk in each container in my sample, and then plot those on a dot plot, this is what this thing would look like. And according to my formulas here at the beginning, the mean of a sampling distribution should be equal to the population mean. And remember, we're going to run the test assuming that the null hypothesis is true. So if that's true, this thing should center at 128 ounces, okay? Now, what we don't know right now, okay, is how far below average. So remember, this is a z-score of 0, right? 0 standard deviations above or below average. Just how far below average would I have to fall, right? Would my sample have to fall for me to want to reject that this statement is true? Now, we are running the test at the 5% level, and it's a lower-tailed test because this arrow is pointing to the left. If the arrow is pointing to the right, then it's an upper-tailed test. And if they simply say does not equal, like here they specifically say, are we not in compliance? And within the context of this question, being in compliant or not being in compliance would be having less than 128 ounces. They could have said, is there evidence to support that the average amount of milk in the containers is not equal to 128? And then I would make the does not equal sign. And I would have to split this 5% area amongst both tails. But since it's a lower tailed test, okay, my rejection region is all going to be in this lower tail. So I'm basically saying if this sample result that we got of 127.2 is in the lowest 5% of samples for this distribution type, we're going to reject the null hypothesis. All right. So here is the lowest 5%. Now, what I'm going to do here first is I'm going to find a critical value. I'm going to say, how many standard deviations below average on a distribution would I have to be to fall in the lowest 5%? Okay. Now to do this, I need to know a couple things, right? I need to know the area to the left of that point. I know it right now, it's 5%. And I'm going to need to know the degrees of freedom, which is always equal to n minus 1. And in this case, my sample size is 12 minus 1, so my degrees of freedom will equal 11. So if I want to find a critical value, a z-score, or I should say t-score, because we're working with a t-distribution right now. All right, this is for means. I'm going to pull up my calculator, and I'm going to hit second distribution, and I'm going to come down to inverse t. All right, if you want critical values for a sampling distribution of proportions, you can use inverse norm because we're taking z-scores when we're doing proportions, but we have to use a t-distribution when we're dealing with means. All right, and I'm going to say, all right, the area to the left is 0.05, and I'm going to say the degrees of freedom is 11, and I'm going to say how many standard deviations below average is that going to be? All right, so if my sample is more than 1.79, let's round this up to 796. If we're more than negative 1.796 standard deviations below average, we're going to end up rejecting. So I'm going to write this critical value, negative 1.796. Okay, here is the critical value. Okay, we have a sample of 127.2. All right, so that we don't know where that's going to fall yet, right? I have z-scores on top, or I should say t-scores. I keep making that mistake. And I have the raw data on the bottom, right? So now what I need is I need a test statistic, okay? I need a test statistic, all right? So I'm going to say, I guess I'll call it T star, okay? And my test statistic is going to tell me, well, how many standard deviations below 128 is my sample that I have. Now, if I go back to my formulas here, in order to do this, I'm going to need to do, what I observed minus the mean for the distribution divided by the standard deviation of this sampling distribution. And that standard deviation is right here. I'm going to take the sample standard deviation divided by the square root of the sample size, right? So in order to find this test statistic, I don't want to get too confusing here. So maybe I won't call it T star. I'm just going to write that test statistic, all right? I'm going to say test statistic, right? Okay, and this is going to be equal to what I observed, right? So we fell short of average, right? The average is supposed to be 128. Our sample fell short of that, 127. We have 127.2. So I'm going to do 127.2 minus 128, which is the mean. And now I need to know the standard deviation of this distribution just to find out, did I fall far enough below average for me to reject the null hypothesis? So they tell us the sample standard deviation, okay, and that was 2.1, 2.1, 2.1, and I'm going to divide that by the square root of my sample size of 12. So my test statistic, let's see, we fell 0.8 below average, 127.2 minus 128 is negative 0.8. So we didn't even fall one full standard deviation below average. We only fell 0.8 standard deviations below average. Now, or I shouldn't say that's not what I meant to say. We didn't fall one full ounce below average. We were only 0.8 ounces below average. We don't know the test statistic yet. That's going to tell us how many standard deviations below average we fell. But before we can do that, I need to know what is the standard error, right? I shouldn't call this a standard deviation. It's a standard error because this is not the population standard deviation. We don't know that. So we substituted in sample standard deviation. So now this is a standard error. Okay. So let's see. I'm going to do 2.1 divided by the square root of 12. And we get this number here, right? I'm going to save this number because I want to be accurate. But just for the sake of my work, I'll put in a 0.606, right? And now I'm going to get my test statistic. That's going to tell me how many standard errors below average is this 127.2. All right, so I need negative 0.8, and I want to divide that by this. Yep. And it turns out that my 127.2 mean for fluid ounces is only negative 1.319. I guess I could probably round this up to negative 1.32. So my test statistic is negative 1.32. Okay, so now I can start to fill in some more information, right? So my 127.2 was not this far away from average. It's actually further to the right. So on the bottom, I can write in, here's your 127.2. And on this distribution, okay, how many standard errors below average was I? I was only negative 1.32. So without even using a p-value, I already know that this is going to fail. This is what I was trying to explain to you guys when I first introduced significance testing, right? I'm not enough standard errors away from the average to fall in this 5% region, right? So if you're going to compare your test statistic to your critical value, if the test statistic is lower than the critical value, it's going to give you a bigger p-value, right? Look at the area to the left of my test statistic. It includes this extra white space, right? The area to the left of my critical value is exactly 5%. So my p-value now, my test statistic is not far enough away from the middle, right? I'm working on the negative side of the distribution. So this number is actually bigger than this number. But if I was working on the positive side, right, if this whole situation was flipped out on the positive side, right, this number would actually be smaller than my critical value. All right, so that's why we don't teach it in terms of test statistic. All right, but you can see this fell in the white region. We're going to fail to reject, but let's use p-value. All right, so one more time, I'm going to have to use I'm going to have to figure out what is my p-value here, okay? So in order to find that, I'm going to hit second, distribution, and let's see here. I'm going to want to use TCDF, okay, because I'm not using a normal distribution. I'm using a t-distribution, all right? And I'm going to say the lower boundary is negative infinity. The upper boundary is going to be negative 1.32. I want this area to the left. So negative 1.32. My degrees of freedom again was 11, and now I'm going to get a p-value. My p-value is over 10%, 0.106, but all I really need, right, my p-value equals 0.106. That is greater than the 5% significance level of the test, and we should be able to see that, right? I'll shade here. The significance level of the test is the red shaded region. Our test statistic is outside the red shaded region. The area to the left of my test statistic is the blue shaded region, and it's 10%. So I'm saying, given that the null hypothesis is true, given that this filling company actually is filling their milk containers to an average of 128 ounces, the probability that I would get this result or worse is 10%. All right, roughly 10%. The probability that I would get a mean in my 12 sample size, right, of 127.2 or less, naturally, just due to random chance, is 10%. Okay. And so it's just not rare enough for me to come back here and say they must be lying. This isn't true. Because there is a 10% chance that given this is true, this could happen. All right. So we just don't have enough evidence to call them out of compliance. All right. We are going to fail to reject. All right. So that is it for a one sample t-test. Let's do a 2-sample t-test. All right. We are going to follow the same procedures that we just followed, basically, to conduct a similar test, but now we're going to do it on the difference between two means. So let's read the question. High cholesterol levels in people can be reduced by exercise, diet, and medication. 20 middle-aged males with cholesterol readings between 220 and 240 milligrams per deciliter of blood were randomly selected from the population of such male patients at a large local hospital. 10 of the 20 males were randomly assigned to Group A, advised on appropriate exercise and diet, and also received a placebo. The other 10 males were assigned to Group B, received the same advice on appropriate exercise and diet, but received a drug intended to reduce cholesterol instead of a placebo. After 3 months, post-treatment cholesterol readings were taken for all 20 males and compared to pre-treatment cholesterol readings. The table below gives the reduction in cholesterol level, pre-treatment reading minus post-treatment reading, for each male in the study. Do the data provide convincing evidence at the 1% level that the cholesterol drug is effective, producing a reduction in the mean cholesterol level beyond that produced by exercise and diet alone? Okay, so here's what we got here. First of all, I'm just going to go right out and tell you that from looking at the grading guidelines from this particular year, if you're somebody whose ears were perking up trying to see if the conditions were going to check, my 20 males, or 10 basically in each group, is too small of a sample size for us to assume that the combined sampling distribution is going to be normally shaped. For this particular question, what they wanted students to do, right? Because they don't tell you in here either that the population is normally distributed. That's why they gave you the raw data. What they wanted students to do was actually to draw some dot plots of this data and say, yeah, the dot plots look approximately symmetric. So it's reasonable for us to assume that the combined sampling distributions is going to be approximately, normally distributed. Okay. I highly doubt they're ever going to have you guys do that again, right? That my bet would be that they'll either give you a sample size bigger than 30, or they'll tell you the population was normally distributed. I highly doubt they would ever give you the raw data and have you check to see if it's roughly symmetrical by showing the dot plots. Okay, so that's one. Now, two, we're running the test at the 1% level, and we're dealing with 2 samples now. So this is going to be how we get the standard error for the combined sampling distribution of X bar 1 minus X bar 2. All right, so let's get at this question now, okay? So this is, now we have 2 sample means, okay? And we're testing to see whether the mean reduction in cholesterol is greater for Group B, since they were receiving a cholesterol drug. So this, of course, is going to be a 2-sample t-test. All right, that's what we're doing. We want to define our parameter. Okay, I'm going to call it MA minus MB for the groups that they were in. And that is going to be equal to, all right, what is it that we're running the test on? We're trying to find the true mean difference in cholesterol. I can't spell. cholesterol. The true mean difference in cholesterol reduction for men who did not take the drug versus men who did take the drug. Okay. And let's just clean that up a little bit. Okay. So that is our parameter defined. Let me stretch that out. And I'll drag that down here. Okay. So we got to check our conditions, right? First condition is, do I have a random sample, right? So first of all, there's my procedure. There. I dragged this down here. It was supposed to be next to this, but it doesn't fit, right? And the mean for group A, or the mean for people who don't take the drug, right? People who are in a placebo, minus the mean for people who do take the drug. We're going to see what's the true mean difference for people who take this drug versus people who don't. All right. So this would be, this is the definition for these symbols over here. But obviously the layout on my page, I can't keep them next to each other right now. That's okay. Does it say in here somewhere that we got a random sample? It does. So random, you would say check. Okay. Also, for each group, we only have 10 men. So like I would say for group A, right, 10 men is going to be less than 10% of the population of men who do not take the drug. And for group B, the other 10 men, we can say is going to be less than 10% of the population of men who do take the drug. So we can check those things off. And then, like I said, for normality, they gave us a sample size that was too small. And they did not tell us that the population was normally distributed. But obviously we have to run the test, right? Because that's the question that they're asking us. So that's why they gave you the raw data here. So you could draw a dot plot and say, yeah, both of these look, approximately symmetrical. So it makes sense for us to run the test. Again, like I said, I highly doubt that they'll do that again. All right. So let me go over to the next page and let me copy over the important information. So for group A, which is the placebo group, all right, we got an X bar. All right, so the reduction in cholesterol for the people, they dieted, they exercised, but they took an inactive drug. On average, their cholesterol went down by 10.2, whatever, milligrams per deciliter. Who cares about that part, really? Right? So let me just go back and double check, right? 10.2. Okay, so X bar for group A was 10.2. And for group B, X bar for their group was 16.4. So they had a bigger reduction in cholesterol. Was it big enough, right? Was it big enough versus what group A did to say that the drug works? Okay. Or is it really not that big of a difference to the point where we could say, oh, I don't know, it could be just random chance due to sampling variability. The guys in this group, they reduced their cholesterol more, but we can't say it was definitely because of the drug because it's really not that big of a difference. Well, that's what we're going to find out. Okay. All right. I need these standard deviations too. So like the standard deviation from sample A was 7.66. They gave us that, 7.66. And for B, it was 9.40. The standard deviation for B was 9.40. Okay, so here's what we got to do here. First, let's write some hypotheses so that we know how to run this test. All right, my null hypothesis is going to be that there's no difference in the average cholesterol reduction between people who don't take this drug, and those are, we're going to say, like people who were in group A, those are like people who didn't take the drug. So the mean difference between the true mean difference between people who don't take the drug and people who do take the drug, those are like people in group B, is equal to 0, right? That's saying it doesn't matter whether you take the drug or not. On average, the reduction in cholesterol is going to be the same. So the difference between the two is 0. And then your all hypothesis basically always depends on what they're asking you in the question. So if I come back, it says here, right? Do these data provide evidence at the 1% level that the cholesterol drug is effective at producing a reduction in the mean level beyond that produced by exercise and diet? Basically, is the mean for the group that takes the drug bigger than the mean for the group that doesn't take the drug? So, right, if I got more cholesterol reduction if I took the drug. So that's going to mean, if that were true, right, the mean of a smaller number minus the mean of a bigger number is going to give us a number less than 0. So this is another lower-tailed t-test, okay? So let me draw in my t-distribution for a second, all right? Let's see. Here's a straight line, okay? And let me try and draw in a normal curve here. Again, it's a t-distribution. I shouldn't call it a normal distribution. It's slightly different from the normal distribution. All right, so here we go. This is the sampling distribution of x bar A minus x bar B, meaning if we conducted this experiment many times and we found the average cholesterol reduction for people not on the drug versus on the drug, and we subtracted them and we plotted them in a dot plot, the sampling distribution would look like this, okay? First of all, the center of this sampling distribution is going to be at 0. Whoops. Because we are going to run this test assuming that the null is true, assuming that there is no difference between taking the drug and not taking the drug. If that were true, then the sampling distribution would center around 0, no difference between the two drugs. And up here, I'll give you a z-score for that. It's also 0, all right? Don't get confused. The mean happens to be 0. The z-score then is 0. I'm 0 standard errors away from average, okay? We obviously observed a difference that is different from 0, and we are going to run the test to see if we have good enough evidence, to see if this difference is actually statistically significant. Now, first thing we got to do is we got to find the critical value. They want us to run the test at the 1% level. Okay, so I need to find the cutoff point here, all right, for the 1% level. Now, I'm going to cheat to find the degrees of freedom, right? The degrees of freedom formula for when you're doing 2 samples, right? Actually, do I have the key for this right now? Yeah, see, here's them wanting you to draw the dot plot. Ridiculous. What degrees of freedom do they say? Something crazy. So instead, we cheat. Oh, see, they say degrees of freedom 17.3, right? And that comes from the crazy degrees of freedom formula that I don't need you to memorize because it's not on the formula sheet. I don't want you to waste any brain power memorizing that. So what I am going to do is I'm going to cheat, and I'm going to hit stat tests. And I want to run a 2-sample t-test. So it's right here, right up top, 2-sample t-test. I'll hit enter. All right. And I'm not, we do have the raw data. Okay. But I don't want that. I'm going to use the summary statistics that we were given. All right. So I can put in all this interesting stuff. First of all, we are running a lower tailed test. So I'm going to change that button here, right? We're trying to see if basically if my mean for my group of people who took the drug is bigger than the mean of people who didn't take the drug. Okay, I want the leftward pointing arrow. All right. Okay, and now I can just fill in this stuff here. Now I know both sample sizes were 10. Right, I'm going to say 10 here. I'm going to say 10 here. Okay, do they ask me the significance level that I want to run this test at in here? No, I suppose not. So that's going to be left for us, right? I guess I should have known that. It's not going to draw the conclusion for us. So what was the mean and standard deviation from that first group, the people who didn't take the drug? It was 10.2 and 7.66. All right, so I'll put that in 10.2 and 7.66. Now, how about the mean for the people who did take the drug and the standard deviation for them? It was 16.4 and 9.4. So 16.4 and 9.4. So I'm actually running the test ahead of time. We're going to get a test statistic and a p-value. We're not going to pool. All right, I'm going to hit calculate. Okay, here's my t-statistic. Here's my p-value. There are the degrees of freedom, right? So I cheated. I didn't need to use that formula to get this degrees of freedom. All right, so now I can report the degrees of freedom to my grader, right? I can write degrees of freedom. Normally it's just n minus 1, but when you're dealing with 2 samples, right, you got to deal with that crazy formula. So we'll say degrees of freedom. Now, I don't need to run inverse T with this degrees of freedom because no, they didn't. Okay, sorry, I do have to do that. I lied. Right? I'm going to take this degrees of freedom 17.2 and I'm going to hit second distribution inverse T. This is all part of making the diagram. All right, and I want the critical value for 1% area to the left with degrees of freedom 17.2. And when I hit paste and enter, calculating. All right, turns out I would need to be negative 2.56 standard errors below average to register in the lowest 1% of these samples. Negative 2.56. All right, you got to show the work. You can't just plug stuff into the calculator, okay? Okay, so our critical value over here is negative 2.56 standard errors below the middle here. All right, we got to figure out what's our test statistic now. Is this difference more than negative 2.6 standard errors below average? And if so, then the probability of it occurring, given that this is true, is going to be less than 1%. Now, just to cheat a little, we actually calculated the test statistic already, right? Stat tests, 2 sample t-test. Okay, here's all the data I put in before. All right, scroll down to the bottom and you're going to see here. Here's my test statistic. Okay, here's my p-value. It's much bigger than 1. My test statistic is not as extreme, right? Negative 1.61, right? Negative 1.61. Let's pick a new color. Negative 1.61 is over here. This difference is not as extreme as it needs to be for us to reject the null. But let's calculate this manually because you're going to have to show these calculations on the exam, right? So we're going to take the 10.2. Here's your placebo group minus 16.4. That is your medicated group. Okay, now what's going to be the standard error for the combined distribution? Again, go back to your formula page. It's equal to the square root of the sample standard deviation squared over the first sample size plus the sample standard deviation squared over the second sample size. All right, so we have those numbers written on our page here. So I'm going to write the square root of 7.66 squared divided by 10 plus 9.4 squared divided by 10. All right, but since the calculator already did it for us, right, here's your test statistic, your t right here, negative 1.61. Negative 1.61. Okay, negative 1.61. We fell in the white space. We have to fail to reject. This difference was not far enough away from the middle of this distribution, in this case 0, right? There's no difference between the two drugs. When I subtract my means, I get 0. We did notice a difference between the two drugs in the samples, but that difference was only negative 1.61 standard errors below average. It needed to be negative 2.56 standard deviations below average or more in order for me to reject the null. My p-value, which I also can pull off of here, right? And you could tell the people on the test tell them you used, the two sample t-test function, and you filled out all this data, and there's your p-value, 0.0619. 0.0619. So think about this, all right? We ran this test at the 1% level, okay? What we found out is the probability that you would get a sample difference of this much, right? 10.2 minus 16.4 has got to be negative 6.2 off the top of my head. All right, so this group had about 16.2 on average more cholesterol reduction than group A, okay? Given that there is no difference between the placebo group and the drug group, meaning the drug does nothing, there's only a 6% chance that we would observe a difference this big or bigger due to random chance alone. So, like in the medical field, I might take that and say there's only a 6% chance that I would notice a difference this extreme or more extreme if my drug didn't work. That's a pretty low number, right? That actually, you would think, is evidence that the drug does work, but they asked us to run the test at the 1% level. If we had to run this test at the 10% level, right, this is smaller than 10%. If they asked us to run this test at the 10% level, you would have rejected the null, okay? But they wanted us to run it at the 1% level. This is bigger than 1%. So your conclusion would have to be that you would, let me see if I can pick one more different color, you would have to fail to reject. Fail to reject H0, right? And the reasoning, the rationale that you would give is because the p-value of 0.0619 is larger than the significance level of the test, right? Here's your 1% area, but the area to the left of here is actually 6%. It's just not an extreme enough difference for me to say that the drug definitely works, okay? So that is t-tests, all right? 1 sample and 2 sample. There it is. Happy studying.